Okay, the stream is on. So, good evening, colleagues. My name is GEORGI ANGELOV, and I'll be the speaker today. So, a little bit about me. I'm a computer science undergraduate at the University of Telecommunications and Posts. I've been programming for like 2 years now. I'm top performing student at the Software University, and you can see my contacts over there. If someone wants to contact me, it's my email, it's my Facebook, and my GitHub. And by the way, the code I'll show today, the demo, will be on my GitHub page. So everyone can see it, everyone can play with it. That's about me. So today we have an interesting topic. I'm not that interesting before that, but I'll try to explain the agenda. Now, I'll try to be as practical as possible. What that means is I'm not only going to talk, but I'm going to do. I have prepared demos, so we'll see how it's actually done. It's not the best demo ever, but it works. It's not perfect. Take it with a grain of salt. Don't use my code in production, because it's not implemented in the best way. It actually is pure trash. Yeah, in industry standards, my code is pure trash. That's it. So, for you to get the best out of this seminar, be focused, and I'll try to explain everything as clear as possible. So if there is something that you didn't understand, just interrupt me. Hands up, I'll answer any question. Even if it's not exactly related to wallets. Even if it's only related to blockchain or, let's say, transactions or elliptic curve cryptography or something in this sense. So we'll try to get a good intuition and a good grasp of the material. It's not that hard, but you need to build a scaffold in order to understand it. We'll go from ground up and we'll build that scaffold. So that's about our agenda. What are we going to talk about today? We have 4 main topics. The first topic is that we're going to I'll introduce you to the wallet. What is a wallet? How it works, what it does, and what are the types of wallets, what services they provide, and how we separate them from each other. We'll talk about HD wallets, and we'll say what is the motivation of the HD wallets. How are they specified? What do they do? How are they different from normal wallets, and how they help? Because that's what they do. They are created because we need help. The old wallets just don't work. They need too much backup and a lot of different shit. I'm sorry. Okay. And at the end, we'll talk about the protocols, because you'll see that HD wallets are actually, they allow you just too much free will. They allow you to experiment and do a range of other stuff. And we'll see that this hinders us when it comes to interoperability of wallets. You'll see that without these protocols, it will be hard for us to create a wallet from, let's say, Jax and import it to MetaMask or something in similar manners. Any questions up till now? Okay, we can continue. Do you know about Slido? Okay, I assume that, not assume, but I know that you won't be asking there because I don't see laptops here, but people that are online, I hope that there are people online watching, they can ask questions at Slido. You just type Slido, I can actually show. You go to your browser and you go to Slido, sli.do. So, you type this code here, just wallets, and it should redirect you to the page. So, you can ask questions as we go through the material, and I'll try my best to answer, if there are any questions at all. Okay, and I hope there are questions, because that will mean that you actually got something out of our seminar. I'll try, this shouldn't be, okay. So, I'll try my best to give you some value, to provide you some value for your time here. It will be 2 hours and a half because we started a bit late, but I'll try my best to provide some value. Okay, so let's get to the point. Introduction to wallets. So, at the core, wallets are just softwares, or wallet is just a software that controls a bunch of keys. And I assume most of you know what keys are and how they relate to the blockchain technology. So, software is just, wallets are just software that use those keys, control them in some way, and store them. That's it. Wallet can also refer to a storage of keys. You can say that I have a wallet file in my computer. And in this wallet file, I have my keys serialized, something like that. It can even refer to a cold storage offline. When you store actual private key in a safe somewhere, that's a wallet.
Can it be said that it's a type of database, so you can have a database file and a database management system, and both are like the active and cold storage versions of the same thing? You have a set of private keys?
Yeah, in some ways you can say that. Yes, the question was, can we say that it's some sort of database that connects the key management and the key storage, every key, and you store them? Yes, in some ways you can say that, but mostly when we talk about wallets, we refer to the software. Yes, and when you talk about wallet files, you actually refer to the serialized keys. And we'll see that when we talk about HG wallets, the serialization process is way easier. Backupping and storing your keys is way easier with HG wallets, and we'll talk about that later. So, wallet softwares, and I'll be referring to wallets as wallet softwares. I'll say wallets, but you'll know that it's wallet softwares. So, wallets are quite similar to today's banking software. Why? Well, because in today's banking software, you have your transaction history, you can send transactions, you can receive transactions, and you can view your balance. That's about it for the banking software. So, as you see, this is Jack's wallet. This is your Jack's wallet. You have your balance here, and this QR code, it doesn't really matter right now what it is. So, you have your Bitcoin amount, and by the way, we don't have accounts. We don't have actual balances in the blockchain, and I'll talk about it a little bit later. So, the wallet keeps your balance. It doesn't really keep it, but it shows you your balance. You can receive transactions. Can you see, by the way? Is it okay? So, you can receive transactions, and you can send ones. Okay, so that's about what a wallet represents. It's just a software that preserves, generates, or stores keys. That's it. And controls them. It creates transactions, it signs those transactions, and sends them. And we'll later talk about that not all wallets do that. And there is a reason. So, it's important, before we continue, we know what keys are. Some people might not know. That's why I've included this in my presentation. So, why are keys so important? And what are those keys? For those who know what actually keys are, I'm really sorry, but we'll just have to include that. So, the keys, or the key pair, is a pair of public and private key. So, they guarantee you claim over the currency. And we'll later see, I think it's on this slide, by the way. We'll see why is that. Why do they guarantee you a claim? And how is actually Bitcoin represented in the blockchain? Because some people might think that Bitcoin is something like you have an account and Bitcoin in that account. But that's not how it is actually. So, here is a scheme. What we see on it is transactions. And why transactions? Because Bitcoin is actually represented by transactions. Do any of you have a clue how? Or?
It exists as the sum of the history of transactions.
Yes, that's right. Yes, that's right. They are not a concrete representation. They exist as unspent transaction output. What does that mean? So, let's say that we have Alice paying to Bob. So, this is the input that Alice uses. It's actually the output, but we'll talk about that after we see what actually this is. So in a transaction, we have inputs and outputs. An input specifies the amount of Bitcoin you want to spend. And keep in mind that if the input references a wrong output, because they are chained this way, as you see, when you make a transaction, you create outputs. And these outputs can be spent. That's it. That's how Bitcoin really works. That's how you represent Bitcoin. You have these outputs, which are called unspent transaction outputs. And every time you want to pay someone, you have to specify which output from which transaction you want to spend. And let's say Bob wants to pay Jonathan. We have the second transaction. So Bob has 3 inputs, and one of these inputs references an output which he has. And this output was generated from Alice. She sent him this output. She created him this output. So, as we said, keys actually guarantee you claim over these outputs. How? Well, we'll see that in the next slide. Okay, so as you see, in the outputs, that's actually the inputs, I think. Yeah, in the outputs, you have something called script public key. What that means is that this is a script that gets executed every time you make a transaction. So, as you see here, we have something called check signature. In order for you to spend this output, you need to specify or actually provide a correct signature. This is something like a check. Yeah, think of outputs like checks. If you don't have the signature, you don't get to spend the output. That's it. So, if you have the private key, it means that you have the pen to write this signature. That's it. And I won't go too deep into this material because it's not really part of our topic. It actually kind of is, but it's a long topic. Yeah, keys overall are a long topic. And transactions. Transactions are like a really, really big topic. So we can't really go too deep. So, as you see, we have an output. Let's say Alice paid me something. And she used some of her outputs to create me some outputs. So I have, let's say she had 3 outputs. She paid me 5 Bitcoin. Now she has 2 outputs. I have 1. And I didn't have outputs before that. Let's say I paid her in cash. So I have this output. But how do I control this output? How do I have claim of this output? How can I claim my Bitcoin? Well, with a private key. That's it. Private keys is just something that guarantees you claim. It's like a pen. Okay, so what happens when you need to spend this output? You have something called script signature. This script signature contains your public key. And this is something like identifier that this is actually you. This is something like an address. Like an IBAN, something like that. Okay, and this here is the signature. This is the actual signature which you generated with the private and public key. So, if this thing is correct, when the actual Bitcoin core or the Bitcoin node or any node validates this transaction, it executes this thing. It concatenates both strings and executes it. And if this thing produces true, it means that this output belongs to you. That's it. And there is no other way to actually claim this Bitcoin without having the private and the public key. That's it. Any questions? Okay, we continue. So there is actually no limit to how many keys you can, how many keys or how much, whatever, key pairs you have. You can have tens of thousands of keys. It doesn't really matter. Everything means, everything just proves how much Bitcoin you have. Like if you have 2 keys, you have claim over 2 accounts. That's it. Okay.
What is the relation between the keys and the wallet?
What are the relation between the keys and the wallet? So, okay, that's an interesting question. The colleague here, one of the colleagues here, asks, what is the relation between keys and wallets? Can I have 10 wallets in a single, 10 keys in a single wallet? We'll talk about this a little bit later, but we'll explain it, how it actually works. Okay, yes, in fact, you can have multiple keys in a single wallet. In fact, you can have infinite keys in a single wallet. It's just the software that controls them. That's it. It doesn't really have a limit, mostly. Yeah, some wallets do have limits, but they're really big limits. So it's almost impossible to reach them. I don't really know what you need to do to reach them. It's a huge number. Okay, so as I told you, the left part is part of the input, and we'll see here that the left part. Come on, what happened here? Okay, it doesn't want to start. Let's start it. So, as I said, the left part of the script is in the input. So imagine here in the input, you have your signature and your public key. And here in the output, you have your locking script. It's called locking script. Why? Because you need an unlocking script to verify that you have a claim over this Bitcoin. That's it. And if you provide the correct signature, you get to spend the output. If you don't, you have no money. That's it. And these outputs are actually saved in a database. You have it's called memory pool. It's not actually a memory pool. It's the unspent transaction pool where the nodes keep them. Every possible unspent transaction output. And this is with the motivation that if I want to find it fast, let's say I make transaction to Bob, and I send the transaction, the node has to find the correct output that I wish to spend. That's it. It finds it, it checks if I have a claim over this output. If I don't, it just invalidates, this invalidates this transaction, and nothing happens. But if I do have a claim, it's okay, you can spend it. It creates a transaction, you sign it, you send it, it validates the transaction, and if it's okay, you spend the output. That's it, and you create more outputs, or less. Do you get it? Okay, let's go to the topic of keys, like actual keys. What are they? Because we were just talking about how they relate to the blockchain. So, as I said, they're just like pens. Yeah, private key is like a pen, and you can sign your checks with it. Okay, so keys are generated using elliptic curve cryptography. Have you heard about elliptic curve cryptography? No, okay.
Question: how I know there are curve parameters that are quantum attack resistant, but is it typical to use quantum resistant elliptic curve cryptography, or is that still not widespread enough?
By the way, the colleague here asks if they actually use quantum resistant elliptic curves, elliptic curves with parameters that are quantum resistant. Yes, I've heard that they're trying, not trying, but there have been talks about specific types of signatures and curves that are quantum resistant, but nothing specific. And SecP 256K1 is the actual elliptic curve used. Okay, let's go to the elliptic curves and we'll talk about more. So, that's the elliptic curve. What is an elliptic curve? Okay, I'll have to write. An elliptic curve is just a set of points. Set of points on the 2D plane. That's it. That's an elliptic curve. And these points have to satisfy a specific equation. And I'll show you how. So we have y squared equals x cubed plus x times a. Come on, x times a plus b. That's the Weierstrass normal form. So this is the equation of the elliptic curve, where y, I shouldn't have done that. So we had y, x, A and B. That's right. A and B are adjustable parameters, as the colleague here told. So these adjustable parameters are specifically chosen for some purpose. Some of the curves are less cryptographically safe, and some curves are faster to compute. Yeah. So the Bitcoin curve uses 0 for A and 7 for B. So the form of the Bitcoin curve, by the way, it's called SecP256K1. It's SecP256K1. That's the Bitcoin curve. That's the name. But this only specifies, the information this brings, it's hard-coded. Okay, I'm not going to dig into elliptic curves, whatever. So the actual form of the Bitcoin elliptic curve is y squared times x cubed plus 7. Why? Because we have x times a, and a is 0. In SecP256K1, x is 0. A is 0. So we get x cubed plus 7. So every time you see a Bitcoin public key represents just a point on the curve. That's it. And for it to be a point on the curve, it has to satisfy the equation. So if you have a specific points, let's say 3 and 4, in order for you to check if it is on the curve, you have to plug in these values to the equation. That's it. So you say 3 squared equals 4 cubed plus 7. And if this holds, it's a public key. That's it. That's everything to it. So what are private keys? They are just integers. That's it. Plain integers, they are not on the curve, they're just integers. And when we talk about SecP256K1, they are really big integers. We're talking about 256 bits integers. That's a huge number. And if you want to create a pair of keys, what you do is you generate a random integer. That's it. You generate a random integer from 1 to n, and n is a huge number. And you multiply that integer by the point. And we're talking here about elliptic curve multiplication. We're not talking about normal scalar multiplication. It's elliptic curve multiplication. It's a specific type of multiplication. It's called group operator. It doesn't really matter now. So what matters is every time you want to create a key, everyone can do it actually. You can just write a simple script to create a key. It won't be secure, but you can do it. You generate a random integer from 1 to n, where n is the, whatever, it's the field size or something like that. I said I won't go into specifics. 1 to n. It's a random integer. You multiply it by the point, and you get the public key. That's it. And the public key is just another point on the curve. There is some theory behind why this is successful, but not going to discuss it right now. Let's just assume that it's true. You can multiply a point by an integer and get another point on the curve. That's it. And as you see here, you can even add those points. That's it. So, any questions up till now? That's about it. So, why do we need those keys? The main reason we need those keys is about the elliptic curve digital signature algorithm. When you have this pair of integer and a point on the curve, you can create a signature that can very hardly be forged. It's almost impossible. People have been successful in breaking 108-bit elliptic curves, but that was super hard. Now, in theory, you can use Shor's algorithm. It's a quantum algorithm that's factorizing integers and what's not, but it's just a theory. Nowadays, it's super hard to break elliptic curves. And thus, it's hard to break the elliptic curve digital signature algorithm. What elliptic curve digital signature algorithm does, it allows you to write the signature on the check. That's it. and no one can forge it. It's thousands and thousands and millions of times harder to forge a digital signature than an actual signature on a check. That's it. Any questions up till now? Okay, we continue. So, some of the key formats. We said that private keys are just integers and public keys are points on the curve. So, in order to increase human readability and to lower the mistake rate, we encode these keys. Let's say you have this huge number, like 100-digit integer. It's really hard to work with it. You need something smaller. So they have thought of a way to increase human readability. So how do they do it? They use base 58 check. It's a special encoding type. Have you heard about base 64? It's something like that, but it's base 58. That's it. It's the... Excuse me?
Does this encoding include forward error correction, as in parity bits and stuff like that?
Yes, I think it's a check. Yes, it's a check. So this is not a simple base 58 encoding. It's base 58 check. You have your sequence, your key, and before you base 58 encode it, you create a checksum. And we'll see later how this checksum is created. So, yeah, you have a checksum and then you encode it. And usually you prefix it with something. You prefix the key with something in order to increase the readability. We'll see that. Okay, so you have your private key. Imagine a random integer between 1 and n. So this integer, after base 58 encoding and some prefix, base 58 check, you get this type of representation. And as you see, it's pretty nifty. It always starts with 5, or K or L. Yeah. That's the WIF format. It's called wallet import format. And that's the usual way you actually handle your keys. You handle them in this format. You don't really work with integers. And it just increases the human readability, and it's not that error prone. Let's say if you want to copy it somewhere and you have this huge integer with numbers and stuff, this is pretty much easier. So we have the BIP32 format, and that's an extended key. We'll talk about this later. It's just another format of a private key. It's some integer encoded in some way. So how do we encode the public key? We had this integer, we encode it in some way. We have now a point on the curve. It's our public key. How do we encode it? How do we... Excuse me?
2 integers.
Yes, these are 2 integers, yes. Thank you. We have a point on the curve. We have x and y. These are 2 integers equally large. Like, they are equally large to the private key. So we need some way to handle them. One of the ways is a raw format. As you see, it's not really pleasant. That's an actual key from a library, from an elliptic curve library. So you have your point x. It's hexadecimal encoded because I don't know why. It's usually done that way. Maybe it's something related to the computations, because with such huge numbers, it's really hard to compute in the... Most of the languages don't really support such huge numbers. One of the languages that support them is Python. You can actually compute huge numbers with Python, but other languages not so much. Yes, that's it. That's right. Yeah, it's efficiency on the bitwise operations. Yes, on the multiplication modulus and so forth and so forth. It's way efficient, way more efficient to work in hexadecimal. So, and usually when we program blockchain stuff, we work a lot with bytes. That's it. And bytes are usually encoded in hexadecimal. That's it. So another format is the compressed format. So what is a compressed format? You get your x point. Where's the x point? Okay, you get your x point and you dump the y. And the only thing in the y you need is its sign. Is it positive or negative? That's it. So you get the sign of the y and you dump it. You just dump it. You don't need it. You get the x coordinate, you prefix it with 0, 2, and add the sign of the y. That's your compressed public key. So why do we do that? It significantly decreases the size of the key. And that's really the key point. But why do we dump Y? You might ask yourself, why is important? Why do we dump it? Why do we dump it? Well, you can compute it. If you remember the form of the elliptic curve, you have y squared equals x cubed plus 7. That's the sec p 256k1. And what you can do is to say y equals square root of the right term. And you get y. That's it. You just plug x and you find y. That's how you uncompress a key. So, any questions? We continue. So, we'll talk about the types of wallets. I assume that up until now, you have a little bit of clarity to what keys are and wallets are. Like we said, it's just a software that controls these keys. That's all you need to know up to this moment. Now, why and how these transactions work and unspent transaction output and every piece of knowledge, we can't really go through it. So assume that we have keys and we have wallets. Keys guarantee you claim over the currency. That's it. That's what you need for the next topic. So, the types of wallets. Ultimately, wallets support 3 types of services. They can generate key pairs, just generating keys. How do they do it? And I told you, you generate a random integer k, let's say k, private. You generate a random integer, that's your private key. You generate a point on the curve. By the way, how you generate this point is you have a specific hard-coded point. It's called the generator point. And you multiply that random integer by that generator point, and you get another point on the curve. That's your public key. Do you want me to show you? Like the actual generator point, or you believe me?
Sure, let's see it.
Okay, let's see it. We go to the Bitcoin documentation, I think. Bitcoin SecP 256k1. Come on, 256k1. Now, how are generator points chosen? It's a different topic. So assume that's something magical. It's just there. There is a lot of group theory and field theory and a lot of unrelated to our topic stuff.
Ugly cryptography.
Yes, that's it. Ugly cryptography. Well, actually, it's beautiful, but for some people, some people are just. You need to focus a lot when you learn cryptography because it's not really an easy subject. And when you actually get the heck of it, when you actually get it, it's really interesting. The way things interact and are created. I'm like, when I was learning about elliptic curves, I was like, dude, people that thought of this are geniuses. Like, you have to be an actual genius to create something like this. That's another subject. Okay, so this is our generator point, I think. Yes, it's called also a base point. And this base point is this thing. It's compressed right now, but it's just a point on the curve. Okay, so, by the way you choose these points, it has to do with the overall number of points on the curve. Just for your knowledge. So we continue with our types of wallets. So as I said, wallets support 3 main types of services. Generating keys is one of them. Spending transactions is another. Like not actual spending, but creating and sending. That's it. As we talked about it, it's something abstract. The transaction cannot be spent. You spend the unspent transaction output, whatever. So, and the last thing wallets can do is to query the blockchain. And by querying, I mean that it just sends RPC calls. Do you know what RPC is?
Remote procedure.
Yes, remote procedure call. It's something like let's say, yes, that's it. You just connect to a peer and you send him some message. Let's say, I want to get this address. It's just like calling a function through the internet. That's it. You send him raw bytes, he deserializes these bytes, and he realizes which function he has to execute and what he has to return to you. That's it. And if I want to get, let's say, a specific unspent transaction output, I just ask him, give me the unspent transaction output for this public key. Something like that. Well, maybe it's not exactly like that, but that's an RPC. So you can query, wallets can query the blockchain. They just send some messages to the nodes, and then they get something back. That's it. And by the way, as we saw, you had an actual balance in your wallet. And that's an aggregated way to display information. It's just every output you have aggregated. That's it. If I have 5 outputs, each of them with 1 Bitcoin, it just aggregates them. It gets every one of them, the wallet, it queries the blockchain, and it just aggregates the data. That's the beauty of wallets. Okay, so we'll see that not all of the wallet types support these operations. So we can split them in 3 categories. We have the full wallet, full service wallet, and as the name incurs, the full service wallet can do all the 3 things. It can generate keys, it can send transactions, it can sign them and query the blockchain. That's it. So we have the sign-only wallet, and you might have heard about sign-only wallets by other name. They're called hardware wallets. Not always, but most of the time they are called hardware wallets or offline wallets. And we'll talk about them a little bit. So we have the distribution-only wallet, which only distributes keys. And we'll see why is that. Like why you actually need to only distribute keys. Let's continue. As you see here, we got the same wallet, Jax. And Jax is a full-service wallet. We saw that you can send transactions, you can generate keys. We are not actually seeing the way it generates keys, but it does it under the hood. So it generates keys, it sends transactions, receives ones, you have transaction history, and when you have a balance in transaction history, it means that it's a full-service node. Because you cannot really get the information from other place than the node. You need an actual node to query. You need to query the blockchain. You can fake it, but it doesn't really mean anything. It doesn't really mean anything. Okay, and here we got a sign-only wallet, also called hardware wallet, which are considered generally more secure because they don't really expose the keys. They are only for signing transactions. That's it. You carry one with you, and you sign your transactions everywhere you want, everywhere you are. Okay, so that's an actual Ledger Nano S. Have you heard about Ledger Nano?
Yeah.
Yeah.
Isn't that just a smart card processor? Like
Yes, that's it. Yes, that's it. They have microcontrollers under the hood. They have a firmware that runs, probably written in C, and they carry your keys, then they sign transactions. You actually send the transaction to your wallet, and it returns it signed. That's it. It doesn't really expose anything. And it has a chip inside. That's it. Okay. And as I said, Jax is a full-service one. So, full-service wallets, they have a full range of functionality. You can query the blockchain. They provide anything you need and anything a wallet can provide. Now, there are actually more sophisticated wallets, but we are not going to talk about them. Like they're still full-service wallets, but they provide way more functionality than just sending raw transactions. That's it. They have multi-signature, complex flow transactions, and so forth, which are beyond the scope of our topic today. So, as I said, we can propagate transactions. And by the way, the propagating works this way. You have a transaction. The wallet creates it, actually. It signs it with your private key, and it sends it to every peer it is connected to the network. And every peer propagates it further. And in a matter of seconds, you get it through the whole chain. That's how a transaction is published. Okay, so some examples of full-service wallets is Jax, Electrum, Mycelium, MetaMask. We'll actually be seeing one of them, Electrum. It's the most simple one in terms of UI, but you have a full range of functionality. It's a full service wallet. You get your balances, you get your transactions, and everything. It actually has a lot of functionality. That's it. That's the Electrum wallet. And that's actually on Mac, but I'll be showing you on Windows. So we have, I pressed something that I didn't have to press. I shouldn't have. Okay, we go back to the wallets. So we got our wallet here, that's Jax. And as you see, you can actually choose which crypto you want to send or receive transactions to or from. And that's the beauty, that's actually the beauty of HD wallets. In simple wallets, which hold just a bunch of keys, you cannot do that. It's almost impossible. And we'll see that these functionalities, now these days, HD wallets are used. The rest of the wallets are obsolete. Actually, the wallets that just store a bunch of keys, they're called JBock, we'll see in a minute, they're obsolete. Nowadays, everything is just a HD wallet. And every wallet here is an HD wallet. MetaMask, Jax, Electrum, Mycelium. They are all industry standard HD wallets. And by the way, MetaMask is one of the most used, so is Jax. Okay, so that's MetaMask.
Which of these listed wallets would you say is the most powerful, as in like
functionality?
really long feature list?
I don't think I would be able to compare them like on a good level, because you really have to play around with them to understand. Like a colleague here asked which one I would say that is the most functional of them. So let me tell you from my perspective, from my experience, MetaMask is the one I love. Like this wallet is super simple. Like in the industry, it's better to have a simple wallet, like simple for the user. It's at the same time secure. You have a simplicity, a good trade-off between simplicity and functionality. And I love that. Like MetaMask is one of my favorite wallets. So Jax, it has a really nice UI. It's simple, yes. And Electrum, maybe Electrum has the most functionalities. I'm not really sure, but yeah, I would say Electrum, or maybe Jax or Electrum, something like that. MetaMask, by the way, MetaMask is mostly Ethereum wallet, because it allows you to publish transactions, not transactions, smart contracts. Yeah, Ethereum is a little bit different, but if you're talking only about the how should I say it? If we are talking about the old currencies, which those that don't really support smart contracts, I would say that maybe the Jax is the better looking one, but Electrum has more capabilities. Maybe. I can't really say with 100% certainty. You'll have to play around with them. Okay, but as I said, my favorite is MetaMask. Jax is not bad too. So the sign-only wallets. What are sign-only wallets? They are usually called offline wallets. And why? Because they are meant for security. They are meant for segregation from the network. You keep them somewhere on, let's say, on a flash drive or on remote laptop. Something that is not connected to the internet. Even the hardware wallet, like the Trezor one or the Ledger Nano, they are not connected to the network. And that significantly improves security. So most of the people that actually trade crypto or buy crypto, they have hardware wallets because they are considered really secure. But nothing is unhackable. I've actually read like huge posts where people have actually hacked hardware wallets. And one of them was particularly interesting. Ledger Nano signs its firmware. it uses signature, the same signatures, maybe not the same, but it uses digital signature to sign its firmware. So if you run an unsigned firmware on your Ledger Nano, it will get detected. That's it. And there was a guy who actually wrote his own firmware. He compressed the old one, and after the state where the software needed to verify the firmware signature, he decompresses the old firmware and gives it, so it can verify the signature. And it returns back the old firmware, it compresses it again, and uses his own firmware. And that was like a really clever attack. But you can hack it. Yeah. And someone can steal it.
Like the PlayStation 3 attack with the US competitors. Like,
I'm not really sure.
the signature check of the firmware.
Okay, I know about an attack of a PlayStation, but I know attack on the actual signature. Are you talking about that attack from the random number generator? No. If I understand correctly, you want to say if that's an attack on the signature, or?
Well, no, I meant he bypassed the use of the signature.
Yes, that's right. Yes, that's right. Yes, that's right. He bypassed the signature. Yeah, he just, it's something like if I have a signed check and an unsigned one, I like fold the signed check and hold both in my hand. And when you want to verify, I get the scrambled one, I unfold it, and I give it to you. And you say, oh, that's my check, it's signed. And you return it back to me. But I fold it again and use mine, which is empty. That's the attack. Yeah, and the PlayStation 1, I remember there was an attack on the signature because they used the same random number. Yes, yes, it was. No, it might have been random, but if you use the same random number, every time you sign something, that's really bad idea because you can produce the actual private key. And if you want to, I can show you. There's actually a meme, I think. PlayStation 3 RNG. Oh, okay. Yes, that's it. That's the random number generator chosen by fair dice roll. Yeah, and if you use the same random number every time you sign, and this is actually separate from the private key. Every time you sign something, you generate a new number, and you sign using that number. And if you use the same key in the signature, yeah, like if you sign something twice with the same with the same random number, you can, from both signatures, you can get the private key, and that's a huge vulnerability.
Something similar to a known plaintext attack, only with the entropy.
Maybe, yes, something like that. You can derive it, yes. Yeah, you know the actual signature, and you compute the private key. That's it. Okay, so we continue. I hope I haven't like spread my thoughts all around. So we're talking about sign-only wallets. Now, sign-only wallets are only for signatures. You have your private keys on them. They don't expose them to the real world. So every time you want to sign a transaction, let's say you have a flash drive, you plug it into your computer, you upload the transaction, you go to your laptop that is completely off the grid, you plug it in your laptop, you sign the transaction, you get your flash back, you put it in your computer that's connected to internet, and you send it. That's it. But that really increases your security, like significantly increased security, because people can actually, if it's like some sort of really super duper malicious hacker, he can read your keys in memory, even in memory, even when they're loaded into the actual memory, he can read them. That's it. Like, I don't really know how this attack. I don't really know how it's called. Yeah, they just read the keys in memory. So, whatever. And that's the only responsibility for the sign-only keys, sign-only wallets. That's it. They improve your security by being off the grid, by providing only signatures. That's it. It's like there is a person in the other room, and if I want a signature on my check, I go to him, and he is hidden. You don't know where he is. He just signs it. I come and I give it to you. Here is the signed check. That's it. Okay. So, and as you see here, there are some wallets. Trezor, I think this one is Trezor. This one. And that's Ledger Nano, and some other wallets that I don't really know. Okay, that's your Ledger Nano. Now, distribution wallets. This is actually a pretty interesting topic. Imagine you have an e-commerce website. Like you have an e-commerce business and you sell stuff, but you're a crypto enthusiast and you have Bitcoin payments or some other cryptocurrency. Now, imagine that you're not an actual security expert and your server, which is at your home or somewhere else, is not secure. So, if you keep your private keys on the server, what happens? People pay you, hackers steal from you. That's it. So, there is actual solution. People have thought of ways to mitigate the risk. So, how do they do that? These distribution wallets, their sole purpose is to distribute public keys. We'll see later that in HG wallets, you can create public keys from public keys. Like you can, it's like I give you a single public key, you can derive thousands and thousands other public keys from it. So imagine we have a public key on our server, only public key. And every time someone has to send us some money, we generate a new public key. And thus, we have control over our private keys, but they are not on the server. And there is still a public key on the server which can generate addresses. Because it's really, how do you say that? Unadvisable or inadvisable? Inadvisable, yes. It's really inadvisable to send everything to a single address. Because if your private key gets compromised, all of your funds are gone. That's why people advise others to, every time someone sends you money or you send, to change addresses.
Eggs and that.
Yes, that's it. Okay, so distribution wallets, they can generate public keys. That's it. And they distribute them in a special manner. And as I said, the motivation is that if you have an insecure environment, you would want your private keys out of there. You don't want them in this insecure, vulnerable environment. That's it. So, as I said, this is allowed only with HG wallets. The normal wallets that store only a bunch of keys, they cannot really do that. Okay, so we can distinguish them by structure. And by structure, I don't really mean actual structure. I don't know why I wrote structure. Let's say we can distinguish them by the ways they create and store keys. That's it. So we have the JBock wallets. And that actually answers your question. The JBock wallet, or JBock, stands for just a bunch of keys. It's a, let's say, a software that has 200 keys in it. It can sign transactions, it can query the blockchain, but it needs to keep track of 200 keys. And it needs to back up them. Because if you lose a private key, you cannot get it back if you don't have a backup. You cannot generate it, because if you actually could generate the same key, Bitcoin would be so insecure that nobody would use it. Okay, so, and as I said, it's super inconvenient. These are considered obsolete because they don't provide the flexibility, they actually require a lot of resources. Imagine having a keychain with 200 keys. Would that be convenient? No, it wouldn't. Okay, that's why we have HG wallets. What do HG wallets do? Well, they allow you to generate infinitely many key pairs from a single one. Imagine instead of having this keychain with 200 keys, you have a single master key, and you can open every door you want. Wouldn't that be cool? And that's it. That's the HG key, HG wallet. You have a single key which you have to keep track of. You don't really need to keep track of thousands of keys.
Could it be said that this operates like a reverse proxy for the addressing of public key transactions? Like every public key you use publicly generated from the master key
Okay.
is like an inbound connection, an inbound HTTP connection, and you want to reroute it to different servers, ergo different keys. So could it be said that an HD wallet is like some sort of proxy for assigning transactions using one key but giving the faces of many keys?
Well, generally, HD wallets do this. They generate key pairs, so you don't really need to keep track of keys behind. You keep track only of the keys you're using at the moment. Like, if you manage to actually, if a key is leaked, HD wallets provide enough security so you can look back. They are there seem to be non-deterministically, when you see them outside of the generation algorithms, they seem non-deterministic, and that's the good thing about it, because it seems that they are not related at all.
Like an anonymized proxy.
Yes, it's something like that. Okay, I hope I've answered the question, if I understood it right. So, okay, as I said, you can produce infinitely many numbers of keys, and that's your JBlock wallet, just a bunch of keys. And that's your HD wallet. You have ways to create, look, this is your master key, not exactly, this is your master key, but from the master key, you can create every other key pair you want, and everything is deterministic. We'll talk about this later. So, okay, let's get into our main topic for today, and that's HD wallets. How do they actually work? How do they help us? And so forth and so forth. And by the way, before that, let's try to start the Electrum one. Do you want to? Okay. Okay, let's see where it's Electrum. Okay, so that's your wallet. You have your wallet here, Electrum. That's one of the full service wallets we've talked about. So, as I started, I should stop this. Okay. Before that, I would like to check Slido if someone has asked a question, which is very unlikely, but I would be glad if someone had. No, there is no question. There are no questions. Okay, so that's your wallet. You have auto connect or select server manually. This means that it asks you if you want to provide certain list of peers, actual peers you want to connect to, like actual IPs maybe. But it has an auto connect, and the way it queries the blockchain for IPs, you have these DNS servers which are called seeders, and it just gets information from them. That's it, like domain DNS servers, and you say to them, give me a list of Bitcoin, of actual active Bitcoin nodes.
Using the actual DNS protocol, is there an actual
I think yes.
protocol query for like this, or
I'm not really sure, but I think they're actually actual DNS servers. Like I'm not 100% sure, but I can actually show you. Do you want to see how you actually get the peers? Okay, we enter the CMD and we say ns lookup. I hope that there's okay. So we have the command ns lookup. It queries a DNS server. So something like that. Not exactly what it does. So we have a Bitcoin seeder. Let's say Bitcoin DNS seed or seeder. So you have a DNS seed. That's what a DNS seed is. I'm sure that we'll find something. We need an actual domain. So. I think I have one here. Let me see. I think it's here. No. It has to be here. Or here. Okay, it's here. I'm certain it's here. So let's open it with Notepad so not to wait. Here it is. That's the command. As you see, here I query for actual peers. That's not completed code, but you can check it out. You can still check it out. And as I said, it's not production code. It's super ugly. Like, are there? Yes, it's proof of concept. By the way, are you? Some of you know developers or JavaScript? Are you familiar? Okay, okay. If you're like, if you want to see, it's written in Node. It's written in backend JavaScript. So, what I do here is I write ns lookup. Come on. Okay, this is it. NS lookup with the domain, and I press enter, and we should be getting it. Oh, it's timing out. It shouldn't be timing out. I think something is wrong. Yeah, well, it should be giving results. For some reason, it's timing out right now, but this should actually give you a list of peers.
So there isn't an actual specific DNS server record type reserved for this. It's just a classic name resolving query for
yes. Yes, that's it. And the actual Bitcore implementation has a couple of those, which it keeps at all times. So it can find new peers. It can query and find new peers. Okay. And by the way, they are dynamic. Like usually, when you're a peer, when you connect to a node and you don't respond for 30 minutes, you just get terminated. That's it. Like it disconnects from you. Yes, something like that. Okay. So we can continue. Where was our wallet? Let's close this one. So let me check the stream. I think there is a sound. So we choose to auto connect, and I press next. I hope that no. Can you see? I'll try to zoom. Okay. So we have our default wallet. We press next, and it asks us, what kind of wallet do you want to create? And as I said, there are more sophisticated types of wallets in terms of functionality. Like the actual sophisticated, as you said, the most functional wallets are those that provide these specific functionalities like multi-signature, like segregated witness compatibility, and things that I don't really know about other cryptocurrency, but about Bitcoin, it's not. Like you can be, it was implemented with soft fork, so you don't really have to. It's backward compatible. Like witnesses are actually backward compatible. So it asks you, what do you want to create? And you say standard wallet, because that's what we're going to use. And by standard wallet, you usually mean HD wallet. Standard HD wallet. So as you see, we have a wallet with factor. Let's change the color. So we have import Bitcoin address or private keys. You can actually import from other wallets. And you have a multi-signature, which we're not going to talk about, but it's basically, it's not only your signature in the input. Like I said, you have an unlocking script, the signature and the public key. And it's not only yours, but it has to be, let's say, 2 of 3. Let's say you have a business, you have a partner, but you have a lawyer also. So if someone like my partner loses his key, we can retrieve the funds. Our lawyer has a backup key. We can sign with 2 of 3. That's it. That's multi-signature. So under the hood, it's a little bit more complicated, but that doesn't really matter. So. And here it asks us create a new seed. Now we're going to talk about the seeds a little bit later. That's part of your master key. Let's say that this is part of. Let's say that the seed is your master key. It's not exactly your master key, but for now, let's say that your seed is your master key. So we choose standard. Yeah, some of them support SegWit. As I said, Electrum is pretty functional. You have SegWit compatibility and other stuff. So press next, and here are our words. We'll later check what these mean. Like these are mnemonic, and we'll talk about them. So we'll press next, and it should generate our wallet. Yeah, and the way it generates the wallet, it generates the master key, and it generates a couple of addresses. Like, it's not exactly a couple of them. Like, if it's a new wallet, it generates, let's say, 10 new addresses. And if you want to send a transaction, it holds the key pairs in memory. That's it. But if you have to back up the wallet, it only saves the master key. And that's the beauty of it. It doesn't have to save every single key pair, because you can generate them from the master key. Okay. Oh yeah, we have to do this. And that's for security. By the way, these words are really important. If you happen to make a wallet, these are super, super important. And you have to keep them really safe. Because in some way, these are actually your key, your master key.
Easy to remember and coding.
Yes, that's it. Mnemonic words. That's it.
A level above basic 4.
Yes, that's it. Yeah, generally mnemonics are used for easy, like if you have some experience with sophisticated techniques for remembering, you can pretty easily memorize those. Like there are people who can memorize 52 cards like for a couple of minutes. Like, yeah. So these are the agenda behind them is that you can memorize them. It's like memorizing your master key, but with more reasonable representation. That's it. So, okay. Well, we have them here actually. Okay. We press next, and we have to, it has to verify them, right? Okay. As you see, we pasted them. It will verify what? This shouldn't be.
Pasted it twice.
Did I? Okay. Yeah, I did. So we have the sequence, and it's not working. Okay, let's write it. It's struck. Yeah, as you see, it's pretty easy to write it, and it's not that error prone. Like if I give you an actual private key or a master key, yeah, master key is just a private key. And if I give you the actual master key, it will be a lot harder to write it. You can make a lot of mistakes, and that's inadvisable because it's actually money you're controlling. You're not controlling something invaluable, something that has no value. Invaluable means a whole another thing, but you control currency, and you shouldn't be making any mistakes. So let's write them. Correct, hurdle, city, foot, language, alone, 12, type, cradle, grass, and long. And we should be done. Yep. So now it asks us for password. And this password helps to improve security of the mnemonic words. Like if I write my mnemonics and store them in my safe, and someone somehow gets to them, he won't be able to actually generate a master key. Because if you have put a password, if you haven't, he will be able. But this is like it introduces more entropy. That's it. So we go and write something like password 12, password 12, and it should generate our wallet. And I hope I can make it a little bit bigger. Okay, that's your Electron. It's super simple. The UI is super simple. It doesn't really matter because it's functional. So as you see, here we have a send tab. You can send transactions. The way you send them is you specify the public key. As I said, the public key is a point. It's like IBAN. You just paste a public key. That's it. So no, actually you paste an address, and the address is generated from the public key. It's a even more human readable representation of your public key. That's it, even from the compressed one. Okay, so generally here you would want to add an address you want to pay to, and you can specify description, which actually doesn't get included into the transaction, I think. But if you have a SegWit, I'm not really sure why description is here, but it doesn't really, you don't really need the description.
The specific currency has a sidechain, right?
Yeah, maybe. Yeah, yes, maybe. If the specific currency has one, yes, that's it. By the way, there is like, have you heard of Steemit? It's really cool. I don't think so. I think it's a full-blown blockchain. But the way, yeah, it's actually, it should be full-blown blockchain because the way they have implemented it is they have JSONs inside a blockchain, and it's super interesting. Like you can have blogs, you can have posts, you can have everything you want into the block, and the block time is like 1 second or 2 seconds. It's super fast and super easy to use.
Flexible data type.
Yes, that's it. That's it. Yes, it's really innovative.
Wouldn't it be more power efficient for like to use Google protocol for like Hyperledger for serialization purposes? Because well, parsing chars, even though JSON is the lightest.
Yes, that's it.
Still
Transmit
high
protocol.
value on high values. I don't know. Maybe it's performance, but
I don't think it's. I don't really think it hurts performance because I've used it and it seems pretty fast to me. Like you can actually see it yourself. It's Steemit. It's actually SteamDB, I think. SteamDB. Yeah, that's it. I am not really sure how they have implemented everything. Like I haven't dug into it, but you basically have these JSONs inside, and you can create, like you can store a lot of data. I really don't know if it hurts, but yeah, it's really innovative because
we have a key value store in the block.
yeah. Okay, so I think that's it. Yes, as you see, you have properties of the JSON object. You have vote, you have transfer, comments. Yeah, you have comments even. Like you can have an actual comments, like really nested JSONs. As I told you, I really don't know much about it. So, but it's interesting. You can check it out. Okay, that's our wallet. We have an amount, and it's specified in Bitcoin because right now we are using Bitcoin. You can send, and as I said, it internally keeps your keys and signs the transaction, and it propagates it to the network. That's what full service wallets do. Now, you have a history here. You can check your history. I can actually send a transaction to myself. There is a Bitcoin faucet, I think. Wait. In order to work with the Bitcoin test network, we need to specify it. Right now we are connected to the main network, and I don't really want to spend money, so we'll say, I think it's testnet, right? So we specify that we want to work with the Bitcoin test network, so we can send ourselves something. It's free, completely free. Like it's meant for testing purposes. Okay, yeah, it's fake money. By the way, I read somewhere that people have actually tried to monetize them. Like actual mining pools, or not mining pools, but people with like a lot of capabilities joined and increased the difficulty of the mining process in order to limit the supply and to actually create something out of it, like actual money. But they have implemented a actual defense against this by resetting the network. Like every 2 years maybe or something like that, it completely resets everything. Like if you had any test coins, you don't have now, and that's really what devalues them. But it's interesting that people have tried to do that. Like there are a lot of greedy people, it seems. So now we want to. I already have a seed. So where is our seed? We lost our seed. That's so unfortunate. Let's create a new one. Okay, we want to create a new seed. Essentially, when we talk about HD wallets, your HD wallet is the seed. That's it. If you want to create another HD wallet, you have to generate another seed. And we'll talk about mnemonics later. Like now it's not really the time. Okay. So we enter our seed and we get the password tab. We write our password. Let's say password 12. No, password 12. Okay, now we can send ourselves some money, some actual fake money. And the way you do that is you go to a Bitcoin faucet, Bitcoin testnet faucet. And what faucet is an actual key pair or an actual wallet. Let's say key pair. Like it's some software that sends transactions to people that request them. Like this wallet has, let's say, 2,000 tested coins. And its main purpose is to distribute them to people. And you just go to the site and you say, give me like 5 test Bitcoins. And it sends you the Bitcoins. It has a private key. It has a key pair, signs the transactions, and sends them to you. That's it. And you already have coins to work with, coins to test. So Bitcoin testnet faucet. You'll see in a moment how it works if you haven't seen one. So that's one of the sites, testnet Manu backend Hamburg. I have no idea why it's called this way. So as you see, it says your testnet address. It asks you for a simple address that you wish to send it to send money to you. Like, let's go to the wallet and get one of our addresses. Okay, so here it is. As you see, that's a receiving. Oh no, I don't think this is an actual testnet address. It should be starting with, I think it can start with N. Whatever. Now, like the address is just a representation of the public key. That's it. Some sort of representation of the public key with a checksum. And it usually has some kind of prefix for you to distinguish them. Because you can't really, if you weren't able to distinguish addresses of, let's say, Bitcoin and Ethereum, it would be like really unpleasant because some real stuff can happen, like something really malicious. So people have implemented them in this way, in such way that you have some sort of prefix that identifies the actual public key. And if you see a public key, if you see an actual address that starts with 1, let's say 1, it's a Bitcoin address. It cannot be anything else. It's either a valid or invalid one, but it has to be a Bitcoin address if it starts with 1. So we get our address here and we specify it here in the address field. So now it will create a transaction to our address and it will sign it and send it. That's the faucet. It just distributes everything. It distributes money. So, and you can see here that it has 22,000 testnet coins. Okay, so I'm not a robot, obviously, or am I? So, and I say, give me some coins, and this should send me some coins. Come on. What? Recaptcha? Oh, cars. Interesting. Okay. We'll specify where the cars are. What? I'm blind, guys. Okay. Let it give me some coin. It's not working. What should we do in this situation? Any ideas?
Refresh, cleaning out the cache.
Which?
Control-Shift-R.
I don't think it's from the cache, but let's see. Like, let's see. Yeah, it's possible. It's actually possible. So, list of prefixes. No, let's say Bitcoin testnet address prefix addresses. So, I think that an actual address starting with them with N is possible, but let's see. Oh, okay, that's it. As you see, we have the testnet public key hash, or the testnet address can start with either M or N. And in our case, our address starts with N. So it's a valid address. We assume that it's valid. It might be not, but let's assume that it is. So we specify our address here, and we say that we're not a robot. Storefront. Okay, we need a storefront. That's a storefront, I think. And that's about it. Is this? Yes, it is. Okay, we verified that we are not robots. And it should send a transaction. It's taking too long, guys.
Well,
Oh, yes.
Bitcoin isn't that quick.
Yeah, we won't be waiting for the transaction. It actually needs
Transaction received.
yeah, transaction is received. As you see, Electrum notified us. And we can see now that we have a history. And it says, you have an unconfirmed transaction. And it actually knows that because it is connected to the network. And only full service wallets do that. So it says you have an unconfirmed transaction and it has a balance of 550 or something like that. It has some amount. Now, in order for a transaction to get confirmed, it has to get into a block. It has to be included in a block. It usually takes 10 minutes, like on average 8 to 10 minutes. And after it gets confirmed, it should notify us. So I won't be closing this, but did you actually get something out of it? Like,
yeah, the transaction's pending, and you can't be sure you actually got the money.
yes, that's. By the way,
by enough nodes, by the miners, or
yes. Usually, it is assumed that transactions that are still not included in a block are still valid for spending, but they carry a lot of risk. So only people who like really receive a microtransactions can assume that these microtransactions are not going to like they are secure, like they are actually secure to spend. But if you are working with a lot of Bitcoin or a lot of crypto, you usually would want to wait 6 confirmations or 6 blocks to stack over yours. Like if actually our transaction gets into a block, it is advisable to wait 6 more blocks before spending that transaction. And
DAG-based currency.
yes, that's it. Yes, that's it. Like the DAG, it hops through the nodes. Yeah. Okay. So as you saw, we have a already sent transaction, and we can actually. I think we can sign a transaction with this output. This here means that we have an unspent output. Someone sent to us, and we now have an unspent output, and we can spend it. We can do that. I don't think it's really necessary. Okay, so we don't really have too much time, so let's continue. As I said, sign-only wallets are sign-only wallets, distribution wallets, and we have our HD wallets now. Okay, so I really wanted to give you a basic overview of what HD wallets are before we get into the specific of how they are actually implemented and how they work. So, as you see, that's our HD wallet. We have a seed, and you saw the seed is actually these words. These words are used for creating your keys. And as you see here, we get this random seed, and we just create a bunch of keys from it. That's it. That's what HD wallets are, fundamentally. So we can derive infinite number of keys, and at some point, you can actually create trees of them, like actual branches of keys. And that's done this way. You have your seed, which is the essential thing of your wallet. It's the core of your wallet, your seed. So that seed creates a master key. And this master key can be used to generate infinite numbers of keys. That's it. You have, like if you generate key with index 0, from it you can generate n numbers of keys. Like it increases exponentially. Yeah, I think it's exponentially. Yes, it's exponential. So you generally can create so much keys. You cannot even, you can never use them all. Okay, so that's what HD wallets are, nothing more. Under the hood, they're a bit more complicated, and we're going to talk about that. And as you see, they are like trees. like actual tree data structures. They have a root and they have nodes. As you see, we have child nodes or child keys, and we have grandchild keys. That's it. And you can generate a new generation, new generation, new generation, new generation. That's about HD wallets. Okay, so the actual definition of HD wallet. What does HD stand for? Because that's really important. Now, H in HD stands for hierarchical. And hierarchical means that you have a master node or root or a root, and from this root you get everything else. It means that everything is generated from that root. It goes from the root down or up, depending on how you want to look at it. Let's say it goes from the root down. You have a master node, and you get everything generated from it in branches. That's it. Okay, so deterministic. Deterministic means that for an input, you get always the same output. That's it. If you have heard of cryptographic hash functions, they are deterministic algorithms. So let's say if I have this seed, let's call it seed. We have the seed, and we create the master key 1. After we create the master key, we can do this infinite number of times. It will always, always, always result to master key 1. You won't get master key 2, master key 3 or 4. You'll always get the same output. That's what deterministic means. For given input, you always, always, always are guaranteed to get the same output. That's it. Like, with some exceptions, but that's about it. That's what deterministic means. So if I have this seed key, let's say I have this master key, I can always generate every key.
You don't need anything else.
Yes, that's right. Yes, that's right. Even you don't really even need the master key. You need only the phrase. And let's say if you have a password, you need the phrase and the password. And it's like going to a big iron door and saying "Sesame." How do you pronounce it? Sesame, sesame, open, something like that, and it just opens for you. It's like a passphrase. You just have this passphrase, and you can generate every single key from it. Your master key and your child keys. That's it. That's the motivation behind. It's the definition behind HD wallets. Now. Okay, previous slide. On which slide? This one? Okay. Yeah. Okay, that's good to mention. So usually you have those BIPs. What BIP stands for? It's Bitcoin Improvement Proposal. It's actually a paper. It's something like a scientific paper in which they propose some improvement for the Bitcoin network, because there are programmers that constantly work on Bitcoin or on blockchain overall, and they constantly think of ways to improve it. So BIP stands for Bitcoin Improvement Proposal. And in BIP 32, there is actually, at the end of the presentation, there is a resources page. You can see links to GitHubs and to books and the SoftUni course, I think. But yes, that's right. That's right. Okay. So you have BIP 32. That's the Bitcoin Improvement Proposal paper, the number 32, which defines the HD wallet. Yeah, which proposes it. Okay. So as you see here, that's a simplistic view of deterministic. You have a single view, and it persists over every device. Like, it doesn't stretch, it doesn't change its layout. It's always the same. That's it. You get it? Okay. So we continue. What is the motivation behind HD? And I assume that you have already built some intuition, but the actual HD wallets are created because it's extremely easy to back up your keys, and you can increase the interoperability between wallets. Like, if I say I create a wallet, I'll be creating a wallet. I'll be calling it Joro wallet, for example. And I say something like, my derivation path will be XXXX. And other enterprise level wallets can say something like, okay, we will support your wallet, and they specify a specific derivation path only for my wallet. So they become more interoperable, and we'll see that in the last topic of our session, and that's about it's about protocols, like actual protocols that HD wallets use. So, as I said, they increase the interoperability between wallets and provide you with easy backups. In a sense that you have a single seed and you just have to back it up. That's it. You have to store it somewhere. So, they also allow for deterministic generation. So every time you load your wallet, it's the same. Nothing gets compromised. Okay, so in order for us to work with HD wallets, we need to have some protocols in place. And we actually have such protocols, and we'll see them later. So, as we said, with this protocol, with the HD protocol, wallets become more interoperable. So, as I said, now imagine you have 2,000 keys in your keychain, and that's such a nuisance. You have to back it up. You need to have a copy for each one of them, and it's not cool. And if you have a HD wallet, you have a single key. That's it, even a phrase. Okay, so the actual core of the wallet, or the main way it functions, is you get this random seed. So you get this cryptographically secure random number. It just generates it. Let's say you get a 32 bytes number. So this number is transferred to a phrase, and we'll later see how that is done. So this phrase is your root seed. This root seed goes through HMAC SHA-512. Are you familiar? Yes, it stands for Message Authentication Code. So the HMAC SHA-512, for every input, it outputs 512 bits of output. So it's a deterministic algorithm, and it doesn't really matter how much information is supplied. It always produces 512 bits, and it's all for every input. It's always the same output. But what HMAC allows you and why it's used? Now, HMAC allows you to add passphrase. If you're using a simple SHA-256, you cannot. You can actually use a passphrase, but you have to append it as a salt. And HMAC provides you a more convenient way to add a passphrase. Okay, so it's a one-way function, and it's super hard to reverse. Okay, as I said, we have this random cryptographically secure number, and you generate your phrase. After you generate your phrase, you plug it into HMAC with a salt or passphrase you supply, like we saw in the Electron wallet. It required that you write a password. Okay, so what happens now? Well, you get a 512 bits output. So this 512 bits output gets split. That's it. So the left part, or the left 56 bits, goes as a master private key. That's your master private key. And that's the whole process. Like, you get your random number, or your random bytes, you turn them into a passphrase, and you plug them into HMAC. You get 512 bits of output. The left part, or the left 32 bytes, you get as a master key. That's your master key. And every time you plug the same phrase and the same password, you get the same output. And thus, you get the same master key. So, as I said, from the private key, you can generate the public key. That's it. Now, you might ask yourself, where does the write bytes go? write bits or bytes. Now, there is something called a master chain code. And master, you don't really need to remember it. Just chain code. That's your chain code. Now, why do we have a chain code? So the chain code introduces additional entropy and additional security. Because let's say you manage, a malicious hacker manages to get a hold of your keys, of one of your private keys. So if there wasn't a chain code, he would be able to generate every single key from that private key. Like if you have, let's say you have your master key and you're using a specific private key in the third subtree. So someone manages to get his hands on this key. What happens now? Yes, and no, not on the master. He manages to get this key. That's not the master. You generate it, that's the second key from the master. Like you have your master key, you generate one and one more key. That's the second private key from your master key. So if he manages to get a hold of this key and you don't have the chain code, he'll be able to produce everything in the sequence. So if you're using the private keys and addresses from this subtree, like if you actually have used these private keys and addresses, he'll be able to produce them. And thus, he'll be able to get a hold of everything. Like everything resulting from this branch will be compromised. That's it. So, okay. After that, we derive the rest of the children in similar manner. That's it. That's what HD wallets do. That's them in a nutshell. You get a random number, let's say 32 bytes random number, and from that 32 bytes random number, you get your phrase, which is, let's say, 24 different words. This phrase you plug into HMAC, and the left part goes as your master key, master private key, and the right part goes as your chain code or master chain code. And that's how the initial process starts. And that's how Electron created our master key. It asked us, it actually, as you saw, it generated us some seeds. It generated 12 words, I think. And these 12 words are our seed. We provided a password, and together with the password, it plugged them into HMAC SHA-512. Left part goes for the master key, right part goes for the chain code. And that's it. That's the initial procedure. Okay, so let's talk a little bit more about mnemonic. As I said, mnemonic, they are just words. Words with the purpose of being easily rememberable. Like, if you create a memory palace, you will be able to generally easily remember them. Like, store them in your permanent memory. And there is a little chance of error. Why? Because they are particularly well chosen so that there are not words that are hard to, like, you cannot mistake one word with another. They're chosen in this way. So it's easy to remember and hard to make an error. As you saw, I was writing them. Like, if you have two pretty similar words, and you might actually get something wrong, and that's bad. Because, like, if you actually make a mistake, it won't hurt you, but it can proceed, and that's the bad thing. Like, you can make an error, but the wallet can still proceed. And that's the bad thing, because you'll have a wallet that's not actually what you want it to have. Like, if you have an actual wallet with money, and you get something wrong when writing the mnemonic sequence, it will give you a whole nother wallet, and you'll say something like, "Where's my money?" You'll be genuinely surprised that your money is gone, and that this results only from your mistake in from the mnemonic. And as I said, they are generally chosen that it's hard to make mistakes and are easily rememberable. So in Bitcoin, these mnemonic words are a list of 2048. That's it. A list of 2048 words. Every single of these words is 11 bits. When you create the random sequence of bytes, you just transfer it to binary, and you slide a window through this sequence of binary, and every 11 bits, you transfer them into indexes. Like if I have an actual 00000001, like I don't know if these are actual 8 bytes, but if you have this number, let's say that's 1 in 00001 in binary, but 1 in decimal, you transfer this, like when the window reaches this sequence, it transfers it to 1, transfers it to decimal, and you get the word on index 1. That's how you actually get the mnemonic. And they are sorted. You have this list of sorted mnemonics, 2048 in length. Okay, so as I said, it's super easy to remember with mnemonic words. You can, that's a simple example with the notes. You can associate every note with a word. Okay, now as you see, this password is something super not convenient. And if you have to remember this, yes, it's secure, but it's really hard to remember. Now, if we transfer it to mnemonic, it's way easier to remember. We have 6, 8, golf, fruit, Xbox, Hulu. Everyone can remember that. Like, there are some specific symbols, but it's way, way more easier than the thing that's above. Okay, I pressed something that I didn't have to press. Let's go, right here. We were here, right? Okay. And these are our mnemonics. So, here's the actual mnemonic schedule. First, we generate our entropy, or our random bytes. That's it. We get 128 bits of randomness. Now, we plug this randomness through a SHA-256. Do you have any idea why we do that? Like, as you see here, we get a 4 bits checksum. Do you have any idea? No, look, you can't really generate nibbles. So, like a nibble is the actual half a byte. Now, if you divide 128 by 11, you get a remainder. So you cannot generate the full sequence. Yes. Yes, that's it. That's it. We have to introduce a checksum, something that completes the bit sequence so you can create the phrase. And as you see, we get the whole thing, which is 132 bits. And from these 132 bits, we divide them to 11-bit segments, and every 11 bits correspond to some index in the list. That's it. That's how you generate your seed. That's the whole HD wallet in a nutshell. Like I said, your HD wallet is the seed. And that's how you create your HD wallet. So, the thing here is that you have this list in memory, and for every window of 11 bits, you get an index. And after everything gets transferred to indexes, you get the sequence. As you see, army, van, defense, carry, jealous, true. It's super easy to remember, no homogeneous words, everything is rather simple. So, and this is deterministic. For every single, like every time you use the same random bytes, you get the same mnemonics. That's it. And as I said, SHA-256 is deterministic. So every time you plug the byte sequence, you get the same checksum. Okay. So, and by the way, if you try to plug mnemonic into third-party wallet, like if you actually generate them with your code and plug them to a third-party wallet, it will use the checksum to verify if the mnemonic sequence is correct. And if, like, sometimes the last word doesn't really, like, if there is something that you didn't implement the right way, it will just say that it's invalid. Okay, so now By the way, before we go to the child derivation, do you want to actually see how mnemonics are generated in actual code? Okay, I might sit actually. So, just for the purpose of the demo, let's go. No, this is too low for me. Okay, so let's see. We open a command line. Let's open it here actually. We open a command line and we say, do you see? Okay, so we say something like node to open the console, the node console. So the interpreter. So we say require. Let you specify a variable. That's it. You allocate a variable. Yes, JavaScript. Are you familiar? Okay. If there is something that you don't understand, just ask. So we say let mnemonic equal require mnemonic. This is requires an actual way of requiring a module, a separate file. Okay. Come on. Mnemonic. Okay. Oh, it's mnemonics. So, what? Yeah, stupid JavaScript. Okay, that's it. So, what? I'm tired of this. So, mnemonic equals this actually. I'll get it a little bit like this. Okay, so we have require the actual mnemonics module, and it's okay. So as you see, we have two functions. Let me, you know what? Let me do this. Come on. Okay, we have two functions. One of them is generate, and one of them is toEntropy. What this means is generate just generates a random sequence of mnemonic, and toEntropy means that you can get this sequence of words and actually get the actual random bytes that you have used. So I don't really think that there is an ID here, but let's see. Let's go to mnemonic. Okay, and we get a visual. Oh, we have a Visual Studio Code. That's super awesome. Okay, and yes, as I said, we have I have a GitHub repository, so you can check it out later. So let's see. We have our word list, and after we have required a module, this word list just populates. You populate and I can actually show it. It's right here. Here's it's as this txt file. These are your mnemonic. These are the mnemonic. This is the mnemonic list. It's 2048 words. They are all sorted alphabetically. So every time you say generate mnemonic, you can specify the strength, and the strength only means the number of words. Like if I specify 24 as strength, you get 24 words. So as you see, we go here and we generate random bytes of the required size. If it's 24 words, we get 32 random bytes. That's it. So this is our seed buffer. Let's actually output it. I think if I write generate, it will output it. Where is the command line? So we say mnemonic generate. Okay, as you see, this is the actual entropy buffer. These are bytes, raw bytes, randomly generated. And by the way, when you make code for production, you would want these bytes to be cryptographically secure, randomly generated. Like using CSPRNG, if you have heard. It means cryptographically safe pseudo-random number generator. Yes, you need cryptographically safe pseudo-randomness to create these bytes. And for everything, not only for the mnemonic, but for absolutely everything that uses random numbers. So we have our actual list of words here. as you see, this is a sequence of words. We can actually do this. We can actually say join and join them. Okay, here it is. That's it. Like stomach, crop, resist, flag, jacket, gesture, so forth and so forth. That's the actual sequence. So how have I created it? As you see, we get our seed buffer. That's our seed bytes. Buffer is something like storage for, it's a storage. Buffer is a storage. So usually when people say buffer, it's bytes buffer, I assume. So additional byte is just the, now this name is really not appropriate, but this, as you see, is hashing the seed buffer. As I said, you need a checksum. So you hash with SHA-256 and you hash the seed buffer. You get the digest. Do you know what the digest is? It's the second name for the actual output of the SHA-256. Yeah, it's called a hash digest or something like that. Yeah, it's a pseudonym for the result. Okay, and I specify that I want it in hex format. So as I get the actual checksum, I need only the last bytes of the result. As we saw, we need only 4 bytes. For 24 words, we need only we need 1 byte. That's it. We need 8 bits for 24 words. So we slice the result, and particularly the first part of the result. Like if you need 8 bits, you will slice the first byte of the digest. That's it. So as we slice it, we get the checksum. And what do is we turn everything, we concatenate both of them, and we get the whole sequence of bytes with the checksum. And what we want to do is to turn them to Boolean. That's it. We turn them to Boolean, like these are some bitwise operations, but the fact is that we turn the bytes into sequence of Boolean. That's it, the sequence of bits. Because I don't really think that JavaScript supports binary, so you have to manually do that. Like you have to create an array of bools. So what we do next, we specify the required length, and if something has gone wrong, we just cry. Like we say, just cry when something is wrong. Okay, so after that, we map every single, as you see, we slice them by 11 bits, and we map every single one. I'm not really sure why I mapped to 1 or 0, but whatever. Like, oh yeah, because it's true or false. Like if it's true, map to 1. If it's false, map to 0. I think there is a better way, but whatever. So we slice them. We slice the bytes to like the bit sequence into windows of 11 bits, and we just map them. And after that, we parse them to integers. Parse them to decimals, and as you see, we say word list of mnemonic index. That's it. And we use this, the windows, the 11-bit windows as index. Okay, and this actually produces your mnemonic, and you return. That's the sequence. The sequence you saw, it's part of this procedure. Like it's the output of this procedure. You get your random bytes, you get the checksum, you turn them to bits, you slide the window of 11 bits. Turn those 11 bits into indexes and get the words. That's it. That's the whole procedure. Everyone can write it. It's actually pretty fast to write. It's not a complicated process. And by the way, I had some problems with the digests. Like if you use different libraries, you really have to get the specifics. Even though like if you're not using it for production, it doesn't really matter, but you generally want compatible results. Like if you go to a popular third-party software, to a popular industry standard wallet, and it generates from a buffer, from a binary sequence, it generates a certain, okay, let's say from random bytes, from the same random bytes that you have generated yours, it generates different mnemonic. It means that something is wrong. And your wallet won't be interoperable and it won't be compatible with them. So you want to check that. Okay. So yeah, we can actually see that our transaction got confirmed. yeah, it got confirmed, and we officially have, I think that's 5 millibitcoin or something like that, whatever. So, and we can actually spend that. Okay, I think that there should be keys here, by the way. Wallet, private keys, seed. Okay, we can actually see the seed. What was it? Password 1, 2. Yes, here it is. We got the seed, it's stored inside, and when we serialize, we just serialize the seed. We don't really need to do a bunch of things. That's just the seed, is the magical seed that produces every single key. And that's all about the procedure of producing the seed. Now, you can actually reverse the process, which is pretty good. And if I say mnm dot to entropy, and I give it the mnemonic sequence, I'll get the actual entropy. That's it. And as you see, if I get this, the actual buffer, and I go to a third-party wallet, let's say something like BIP32. I think there are a lot of BIP32 compatible JavaScript wallets. We go here and look, you should be careful. Like, as you see, this uses HMAC SHA-256, and yeah, it will always produce different thing. Yeah, you should be aware of that. So there should be a cool wallet here. Okay, that's it. It says input your own entropy. So you say base 16 or hexadecimal in other words, and you specify your, yeah. So let's see. It should be 24 words. Generate new phrase. So as you see, it's the same thing. We get the same mnemonic words, and that's how it should happen, because we want interoperability between wallets. Okay. So, and we can actually check if the keys are the same, by the way. So, just okay. Now we can proceed with the child derivation. So, as I said, we add a master key, so we can derive multiple children from it. But how it is actually done? Before that, as I said, the public key, the public parent key, can be serialized, or the uncompressed version is just the x and y coordinate prefixed with 0.04 byte. That's it. It's a single 4. Okay. So the parent chain code is the data that increases the entropy, increases the security. So we can see here that this is our parent private key. And our parent private key can be used to generate our parent public key. And I say parent private key because as you might already have like figured out, the procedure is almost the same everywhere. Like if you have an actual master key, the procedure for generating a private key is the same as the procedure you would use for like private keys that are far away from the master key. Okay, that's why we call them parent keys. So we got our parent key and we got our parent public key. How do we create the child key? Now, every child has an index. It has to has it needs to have an index because that's how you differentiate them from one another, and that's how you create unique ones. So every child can be from. You can actually have from a parent key. You can have 2 to the 32 different child keys. That's it. It's an integer. You can have an unsigned integer as an index. That's it. Okay. So. But we also need our chain code. So how do we do that? Now, this is the standard procedure of creating child private keys. You got your parent private key, which is 256 bits, and you have your parent public key. Now, you plug your parent public key and your parent chain code into an HMAC together with the index. That's it. So you get your parent chain code and your parent public key, which is generated from your parent private key, and your index, and you plug it into HMAC. Now, as we know, the left part goes as child private key, like as an actual private key. And the right part goes as a chain code. That's it. So as we see, the child chain codes get deterministically generated from the parent from the parent chain code. That's it. Okay. So as I said, you can produce up to 2 to the 32 children. Okay. So by the way, outside in the real world, like outside the wallet structure, outside the key derivation function, like the actual, let's say the child derivation function, every key seems non-deterministic. And this means that if you get a parent key and a child key, there is no way to connect them. Like you would actually think that they're completely different, separate from each other. And you won't be able to realize that, if you don't know, that they are parent and child. Yes, that's it. Okay, so, and the usual abbreviation is CDF, a child derivation function. Okay, so, even the chain code improves the security that in cases that someone gets a hold of your key, he cannot generate and compromise the whole branch. Like, as I said, if we have an actual master and a parent private key, and someone gets a hold of this private key, if he doesn't have the chain code, he won't be able to create children. Because as we saw, the HMAC takes the chain code. It needs the parent chain code to produce the children. That's it. Okay. So, what we call extended private and public keys. Now, this term might seem like strange to you. Say, good, more new terms, like this is so good. Okay, but it's really not complicated. Extended private key or public key is just the public or the private key with appended the chain code to it. That's it. That's your extended public key or private key. And why do we call them extended is because they can actually offer you extensibility. You can create more keys from them. Like, if you have two keys and one of them is extended and one of them is not, you'll know that from extended one, you can create more keys. That's it. Like, let's say you have two identical private keys, and the second one is extended with the chain code. And that means that it is an extended key, and it can create more children. But the left one, which is identical but not extended, which means that it doesn't provide you with the chain code, it cannot extend itself. That's it. Okay, so as we said, there can be public extended keys too. And public extended keys too are the same thing. They're just the public key with appended chain code to them. Okay, and as I said previously, they are usually base 58 check encoded. And they're prefixed with special bytes, so that every time you encode a key, you get a specific version, you get a specific prefix. That in the concrete example here, like the actual extended keys are always prefixed with X private and X public. If you have, like if you create an actual software for computing these keys, and after you base 58 encode them, your plain keys, and you don't get X private or X public, there is something wrong. Because it has to give you this prefix. Okay, so as I said, think of, I actually didn't say that, but think of the extended keys as branches, like a root of, it's a root branch. That's it. You get, you basically have a whole subtree. That's it. You have a subtree which is a part of the bigger one, but it's like a separate entity. Okay, so Here are some examples. We got X private and X public. These are two keys. As you see, they are pretty big. Like these are 512 bits. And imagine if you had to brute force that. Like that's completely impossible. So, okay, we have X prive and X public. These are the keys. Extended keys, which every time you see this and you see the prefix, you know that these keys are extended, you can extend them. And that's the beauty of it. Okay, so, but there is a slight problem with that. Can you think of something? Like, if someone actually gets a hold of your key, of your public key, wouldn't he be able to get your actual chain code? Like if he gets a hold of your public key and your chain code, he can compromise. Like, yeah, basically this means that if someone gets your public key and chain code, he can derive your private key. That's it. Because as we saw, the private keys are generated through the public key and parent public key and parent chain code. But if someone gets a hold of them, of the both of them, he can derive the private keys. There are defense mechanisms, and we'll discuss them in a moment. So, as I said, deriving a child public key from an extended public key. That's we were discussing previously the distribution-only wallets, and that's how they do it. As we said, we have a private key, we have a public key, and this public key can generate unlimited amounts of public keys, and that's because they are extended public keys, and we'll see that in a moment. So we see here that we no longer create private key. Like the left part of our HMAC goes directly for a public key. And that's a way that if you are in an insecure environment, you separate your private keys from your public keys. So no one can actually compromise them. If you're on an insecure server, you would want this type of generation of a child. You would want to generate new child public keys from old parent public keys. And that's how it's done. You get your parent public key, and you get your parent chain code, and you get your index number. That's it. You just generate a next child, a child in the next tree. So you plug it into HMAC SHA-512. The left part is your child public, and the right part is a child chain code. And this can be extended many times, unlimited amount of times. Okay, so as I said, you can only derive extended public keys from parent public keys, parent extended. Yeah, this is something like a protocol, like a rule, that you can only derive extended public keys from parent extended public keys. You cannot, in example, derive a private key with only having the parent public and the parent chain code. I hope you get it. Okay. So, as we said, there are some security risks, and they have been considered. There is a special index range from 2 to the 31 to 2 to the 32 minus 1 that provides us with the special types of keys, which are called hardened keys. And why do we need them? Why do we need this special range of keys? And they're special also because the generation is different. Like, I'll try to summarize it after that, and I'll think that you'll be able to get something out of it. So, okay, as I said, we have a special number of indexes, which range from 2 to the 31 to 2 to the 32 minus 1. And these special number of indexes, if you derive childs from them, like if I derive child from index 2 to the 31 plus 1, these are called hardened childs. Why are they called hardened childs, and how do they work? Like, they work differently, obviously. But there is a specific reason why this exists. So let's say that you manage to get a hold of a public key and a chain code and its corresponding key. Like, let's say the example with e-commerce again. Someone gets a public key from you, and you say to him, like, send me to this public key the money. But he's a malicious hacker, and he somehow manages to get the private key corresponding to this public key. But now he has the chain code, the public key, and the private key. Thus, what he can do is he can compromise the whole chain, and even if he has a parent chain code, he can derive parent public key, a parent private key, which is super, super insecure. So people have thought of ways to mitigate that risk, and that's with hardened keys. These are the keys from 2 to the 31 to 2 to the 32 minus 1. And by the way, this is the motivation behind this index range is that you have to somehow separate them from the rest keys. If someone gives you, like, derive for me child key number 208, you'll know that that's not a hardened key. But if he says to you, derive me child number 2 to the 31 plus 1, you'll know that this is hardened key, and you'll use different procedure. That's it. That's why the indexes are different. Like, it's a whole different, it's a reserved range. That's it. So, if you remember, the last time we saw such a diagram, it's actually, I don't think it was the last time, but the first time we saw such a diagram, it was you could generate from the public key and a chain code a private key and a chain code, right? But this means that you have to use the actual, no, okay, I didn't get it right. So this means that your public key, you are deriving a private key from public one, which is not advised. It's insecure. And as I said, if someone gets a hold of private, public, and chain code, he can actually derive the parent private key. So what do we do in such situations? We derive hardened childs. So what does a hardened child mean? As you see, hardened child is created from a parent private key. It's no longer public key, it's private key. It goes through the HMAC, and the chain code goes through an HMAC. These both account for the 512 bits output. And this way, you separate, you generate the actual keys from the private ones. Like, you generate an actual child from the private key, not from the public one. And private keys are generally way more secure. Like, you keep your private keys safe. That's why they are called private keys. And this way, like, you are separating this child key in its chain from the parents. That's it. That's why hardened keys exist. You would want to separate the subchain from the parents. So they cannot, even if they get a hold of the chain code or the parent chain code, they cannot generate your private key. That's it. Okay, so as I said, hardened derivation breaks the relationship between the parent public and the child chain code. Yeah, we no longer have a relationship between the public and the, okay, so imagine now we get a hold of the public key. As you see, we cannot derive the next. Like, okay, we get a hold of this one, like the child public key and the child chain code. But we cannot, we no longer can compromise the whole subchain. If we try to derive from this, it won't happen. Why? Because it no longer uses public keys to derive more keys. It uses private. That's it. We cannot generate hardened childs. Okay. So yeah, the hardened keys are actually a security-wise measure. That's it. So Before we continue to the compatibility, we have a little bit left of the presentation, but I would like to show you something. So we go to the next script, and that's the BIP39. We talked about BIP39, and I assume you already are familiar that we generate a master key from the mnemonic sequence and a passphrase, and yeah, they go through a special function. So what I omitted, like what I didn't say, is that after you get your mnemonics and your salt or your password, it goes through a specific key derivation function. And that's called PBKDF2. And that stands for password-based key derivation function 2. And that's actually an industry standard of key derivation functions. Like, it's actually used in production. It's a pretty good one. I think that NIST recommend them. So, as you see, the way we actually transfer the mnemonic sequence in the passphrase into a master key is we plug it into this PBKDF2, or this function. This is a key derivation function, and the rounds that it performs are 2048. And the way you remember it is just that's the size of the list. That's how I remember it. It's hard-coded constant. Yeah, that's how many iterations wallets use with the PBKDF. It's hard-coded. You can remember it that this is related to the size of the list of the mnemonic words. So we specify a size. We get a size that's 64 bytes, and we specify that we'll be using SHA-512. Okay, that's it. Like, that's the actual seed generation. That's the actual seed key. So let's go to another BIP. We'll actually see what this does in a moment. We go to this one, that's BIP32. As I said, BIP stands for Bitcoin Improvement Proposal, and it usually specifies, the BIP32 one specifies the HT protocol. So you can actually check it later. Now, what we have here, as you see, it's a pretty big script. More comments though. Okay, here is our seed key. We generated our seed key, or this is actually our seed. But instead of only a mnemonic sequence, we plug the mnemonic sequence and the passphrase into the password, into the key derivation function. And this key derivation function introduces more and more entropy. And now we have something completely new, something completely random. Yeah, not completely random, but pseudo-randomness. Yes. Okay. What do we do now is, as we said, we plug it into HMAC. And you can actually deduce what happens next. We get the left part as a master private and the right part as a master chain code. That's it. That's how the master keys are generated. And I actually show you that. So we go to the, let's change the font. I think it would be better if we downsize a little bit. So let's go here. Come on. Okay, properties. I think this is okay. Like, can you see? Okay, so what do we do now is we create a BIP. We require the BIP. So we require the actual, okay, we require the BIP32 module. So after we require the BIP32, it will automatically inside create the mnemonics. That's it. So now what we can do is say, create me a new wallet. Like let wallet, it's just a variable which holds the wallet. So BIP32, it's a constructor, like it's a function, constructor-like function. So we specify the name of the wallet, and I won't really go into specifics, but that's related to the serialization. Like the name of the wallet actually later helps to find the actual file. So, and by the way, the actual key store file or the wallet, the serialized seed or wallet is heavily encrypted. Like they encrypt it really, really heavily. And I can show you later. So BIP32, and No, that's not it. So my wallet, that's the name. That's the name of the wallet. And we can specify a password. And our password will be my pass. That's it. So we specify that this is a generator. Now, generator means that it will create new wallet. That's it. Like if I specify that it's a loader, it will assume that it has to deserialize a wallet and has to use already created one. So yeah, that's an implementation specific. But you generally have a lot of freedom. Like when we talk about HD wallets, you have in BIP32 you have a lot of freedom, and it's not necessarily something good, but we'll talk about it later. So as I said, we got the generator, and it spits out the mnemonic. That's the mnemonic, and from that mnemonic, we get the password I provided. We plug them into the PBKDF, and we get the seed. That's it. So from the seed, you plug it into HMAC. The left part is master key, private master private, and the right part is the master chain. Now, the master key, the master private key, the master chain code, both get appended together to produce the actual master extended private key. That's it. And from this key, everything results. So, okay, let's see. When I write wallet, we got a couple of functions. We have a function derive, serialize, to extended key, and get mnemonic. Now, get mnemonic, that's okay. Like everyone knows what that is at this point. So, to extended key means that it will base encode it, base 58 encode it. It will just, in some way, it will create a more humane key. And we can see that. Look, now, if we say wallet.derive, it will actually show me the master key. So, this is the actual master key. And I will later show you that if you plug it, if you plug the same mnemonic sequence and the same passphrase into the online wallet, it will create the same master key. So we have our key and we have our chain code. That's it. That's the left part and the right part of the HMAC. And here we have a parent fingerprint. Now, generally, parent fingerprint for the master key is just 0 bytes. But it's something like it's actually a fingerprint. Like you actually can see which parent produced this child. Because when you produce the child, you plug the master key into, you plug the parent key into a SHA, you get the checksum, and you use it as a parent fingerprint. So every time you plug the parent, you can see if that's the correct parent. That's it. I assume that this is why it's there. So, as I said, we have an index. And here, it's just called child number. And we can have 2 to the 31 childs, 2 to the 32 minus 1. And we have a depth. And depth refers to the depth in the tree. Like, if you have an actual master node with three private keys, and you are right here, you have your depth 3. Or 2 maybe, if you start from 0. 3, okay, let's say 3. The depth is 3, that's it. And this is good because at some point, you would want to stop generating keys. Like, you cannot go infinitely. Like, infinite depth, that's not really convenient. So, let's say you specify that the max depth is 20. And if you reach that max depth, you just stop. That's why it's there, maybe. So, and this is just a boolean that specifies if this is a private key. And in our case, it is. It's our master private key. Now, let's get it into a variable. So, we have our key. What can we do with it is to base 58 it. We can say to base 58. Look at what we got. That's our key. That's our base 58 encoded key. Prefixed with some prefix, like some bytes appended to it, and it has the prefix is X private. And from the length of it and from the prefix, we know that this is extended private key, which means that it can derive more keys. Okay, I assume that you got this. Now, what can we actually do is to create an address. We can say to address. I don't think it's called to address. Let's see. We will need to open the extended key file. Okay, yes, we can, oh, you know what? This is not the public key. This is the private key. We cannot, yeah, we cannot create an address from the private key. Okay, so we say public key bytes. Public key bytes. Okay, that's our public key. Now I would actually want to get an actual object, so I'll see if I can do that. But as you see, if it's prefixed 02, it means that it's compressed. This is only the X coordinate. This is the master public key, and it's compressed. That's a compressed format. Now, if we want to extend it, we would need to have the chain code, and that's what separates the normal keys from the extended ones. They have the chain code. So, let's see if we have we actually have the functionality for this. Public key bytes. Okay. Yeah. You can see that here we're just multiplying our private key by the point. That's it, and you get another point. And as you see, we say compress my point. So we dispose of y and we append 02. Okay. So we go. We need a public key. Okay. We have two address. Yes, we have two address. Okay. Now I'll just derive a child key to show the address thingy. I think I'll be able to. Not really sure. Okay, let's see if there is a functionality that lets us. Oh, we have derive extended public key. That's cool. Derive extended public. Is that how it's called? Extended public key. Okay, we got it. As you see, this is the compressed public key, and this is our chain code, which means that we now have an object with the extended public key. Now we can say that this public key has to be an address. What? Oh, it's BIP30. No, it's actually. Yeah, it's static method. We cannot use it this way. I assume you know what static is. Yes. Let's require the actual extended key class. So we say extended key equals require to the extended key GS. Extended key GS. So what? Oh, I didn't write it properly. Extended key GS. Okay, extended key dot yeah, to address. Extended key dot to address, and we get our. Oh no. Okay, you know what? We don't have the variable. Let's say public key equals k time k2 extended. What was it? Extended public key. What? This shouldn't be like this. 2x. Oh, derive. Okay, public key equals k times k dot to derive extended public key. So we have our public key here. Now what we can do is we say extended key. Okay, extended key dot to address of our public key. Here it is. We have our actual address. I don't really know what's prefixed with 5, but as you see, it's a lot less bigger. Like if the actual extended public key was, let's say, what, like, I think it's there 512 bytes or something like that, bits, and this one is really less. So it's really easy to work with the address and not with the public key. And by the way, when we talk about blockchain, the public key, the first time it actually gets to the public is the time you spent an output. That's it. Because in an output, you don't specify your public key. You specify your address. And as I said, you use SHA-256 to create the address, so it's irreversible. Yeah, presumably irreversible. So you cannot create a public key from the address. But after you spend the transaction, you actually need to provide your public key. Okay, so that's it. That's all about the actual master key. And now we can, as I showed, we can derive extended public keys from the private ones. We can actually extend the private with new private key. We can derive a new private child from the old private key. And we can do that by saying k.derive child, let's say 512. And we'll get the 512th child. And as you see, it actually has a parent fingerprint. And if you see the public key here, it doesn't. Oh, this is the private, I think. Let's see. Oh, okay, here it is. Like the parent master key, like the master private key and the master public key, they don't have parent fingerprints because they are the master ones. So down in the chain, you get a fingerprint, and that's it. As I said, it's just a checksum from SHA. So you can identify this key with a parent, if you have to. So as you see, it's another extended private key, and you can extend it infinite number of times. So let's see what kind of functionality it also provides here. Let's go. I think there is something else. Okay, you can see here that if we actually have the x from this equation here, let me zoom a bit more. From this equation here, I assume you can see it. Yeah, you can derive the y coordinate. So you don't really need it. That's why mostly compressed public keys are used, because they're a lot shorter and you don't really need to carry the y all the way with you. So we got an out of corridor. That's not really important. The compressed point. Yes, that's all about the functionality. Now, we talked about that there are three types of derivation. One of the derivation was from public parent key and a public and a parent chain code. We derive a private key and a chain code, new chain code. But as we said, this compromises the security because there is a relationship between the private and the public key, the child private and the parent public, and that shouldn't be done, because if you get a hold of this parent public key and the chain code, you can compromise the whole chain. Now, this is where the hardened keys come, where you break the relationship between the public key and the private key, the parent public and the child private. Thus, you are able to create child private keys from parent private keys. There is a way more security here. Now, the last way for generating was from parent public to public key. That's it. And we're talking about extended keys. Now, this also provided us with some, like, we are also prone to security attacks, like security vulnerabilities. So we should be careful. But these three types are generally the types we use for child derivation. And you can see this way. We have three cases. And you can see it right here. I will actually zoom. I will try to zoom. So if we come here at derive child key. Okay, derive child. So as you see, we are having three cases. The first case is if the key is hardened. And that, as I said, it's just a range. It's a sub-range of integers or of indexes that specify hardened keys, just to be able to distinguish the procedures. So if our key is hardened, what we have to do? Well, we have to derive private key from the private key. That's it. We have a relationship between the parent private key and the child private key. That's the hardened derivation. The next type of derivation was the public key. So as you see here, if the key is hardened, if the parent key is hardened, we just concatenate a 0 byte with the private key. That's it. And we use the HMAC 512. We get the left part as master key, the right as a child key, the right part as a child chain code. That's it. So, but if it's not hardened, we need to use the public key. That's it. There are two ways. There are two possibilities that will be using the public key and one possibility that will be using the private key. And as you see here, if it's hardened, use the private key. If it's not hardened, use the public key. That's it. So after you get this data, you add the index. As you see, you write to the buffer the index. That's it. You don't really need to know how it's done. You write the index to the buffer. So after that, you HMAC everything. You get the left part and the right part. That's about it. That's about the procedure. So as you see, if the key is private, you use the specific procedure. You decompress the public key and do some calculations in order to be able to produce a public key from the public one. That's it. Okay, so that's about it. If you have any questions up until now, and I'll try my best to go fast through the last part. Now, as you see, there is a lot of flexibility. Let's say you create a wallet and I create a wallet, and the people that are using your wallet, for some reason they are unsatisfied, and then they want to come to me. But if you have used a completely random derivation path, and by derivation path I mean the path through the tree, for their keys and for their addresses, it will be super hard for me to replicate that. Let's say we have a tree, and the way you have generated their paths or keys is completely random. Like, let's say you take this path, you go to the right, then to the left, and so forth and so forth. And I go to a completely different part when they import their seeds. And this results in non-interoperability. These wallets are no longer compatible. And for that, we have specific protocols which are specified in BIP 43 and 44. And the way these protocols work is they specify a certain, they give a meaning to every index in the stage. So we'll see that. Now, the first index is a purpose. If you see, this is your master key. That's generally, this is the way you specify your derivation path. And M only means your master key. That's your master key. And 44 here means that this is the 44th index. Now, BIP 43 specifies that the second index, or the first index from the master, should have specific purpose. And this specific purpose, when it's 44, it means that wallets that derive from M44 are BIP 44 compatible. That's it. Like, let's say you're creating a wallet only for charity, and you have a wallet only for, well, it's not exactly like this, but let's say that there is a subset of all wallets in the market that support different things. Like they work in a different way. So they can potentially define their own purpose index. Like if you and we want to create something like our own way to create keys, we can say that number 153 is our purpose index. Everyone that wants to join us can derive his key from 153rd index or something like that. That's the purpose. And this exponentially increases our chances of interoperability. And we'll see why. Now, as you see here, 560 is just an example. Yeah, if you derive from M560, it can mean that you support BIP 560. And you work with the BIP 560 protocol. Okay, so this is the more important part. Now, BIP 44 specifies a way more specific way of derivation. Now, what is this way? as we said, we have purpose. By the way, if you see such a subscript, it means that it's hardened key. Like, if you see something like 0 and a subscript, it means that this is 2 to the 31. And if you see a 0 without a subscript, it means 0. That's it. Like, the key ranges are split from 0 to 2 to the 31, and from 2 to the 31 to the 2 to the 32. Yeah, -1. That's it. Okay. So first, we have our master key. And this here is called the derivation path. This is used for interoperability. Otherwise, it's too much freedom. It gets really hard to get compatible. So we have the purpose index. And after that, like we specified what purpose index is, we have a coin type. Now, if our wallets work with purpose 44, let's say purpose 44, that's the purpose that indicates that you support BIP 44. If our wallets derive from 44, the next index we have is a coin type. And in example, 0 index means Bitcoin. Index 1 means Bitcoin test. And maybe index 44 can mean Dogecoin or Litecoin. And that's it. It just specifies which coins work with which indexes. And that's really important because you don't want to mix the addresses of the different crypto. Okay. So after that, you have, and by the way, as I said, these are hardened. The first 3 indexes are hardened. That's a standard. So, and we are using these standards to increase the interoperability and being able to have compatible wallets. So this is our account. And our account just separates every single, like, if you want to have multiple accounts in a single wallet, HG wallet, you can have that. Like, one of the accounts could be your savings. One of the accounts could be like charity fund or something like that. One of your accounts can be business-specific account. And this is good because you separate the responsibilities of your accounts. And that's what accounts stand for. Like, if you have, you say that account 5 is business account, and every time you want to create, you want to see the balance and get the keys and everything, you just specify the specific derivation path. And you know that account 5 or index 5, key index 5 is the root of your business chain. That's it. Okay. So, as you see, you can make donations, you can have a savings account, business account, and everything else. So, change. What is change? Specifically, when we talk about change, there are 2 hard-coded values. It's 0 and 1. 0 is called the external chain. I might actually mix them up, but whatever. One of them is the external chain, and one of them is the internal chain. 0 and 1, 2 indexes only. And what do they mean is that the external chain is used only for sending, for receiving payments. Like I said, you have an e-commerce website or some sort of distributed or decentralized market, and you want to pay someone, he will use, if he has a nice wallet industry standard, he'll use an external chain. Let's say, okay, let's give an example. You have wallets that are compatible with 44 BIP. So the purpose is 44. You have one as test Bitcoins. Okay, and you have some sort of account. Now, you want to receive a payment. You go with index, let's say 0. That's your external chain. And the address index here, the address on which you'll receive the payment, it's just some random index. It could be 100. But with this specific derivation path, every time you import this wallet, the wallet you import to will know that your purpose is 44, your BIP 44 compatible, which means that your coin type, the coin type you'll choose is probably Bitcoin test, and it will know that it has to use 1. That's it. So nothing gets lost. You can always derive the same change addresses. That's it. So you'll specify the account, and it will just query the change. That's it. You usually specify these 2 from the interface. Like in terms of jacks, you just choose the right crypto in your account. That's it. Okay, and it just queries the change and looks for currency. And the last thing, as I said, is the address index. You have some sort of address. And when it's on the internal chain, this chain is meant only for change addresses. Like when you spend Bitcoin, like if I spend 5 Bitcoin and pay you only 1 Bitcoin, I can route the rest 4 Bitcoin to another address. I cannot retain them to the same output. I have to reroute them or send them to another one of my addresses. That's how it works. So the internal chain is used only for change addresses. That's how they are called. It's like how you give a $5 bill and you get like I pay you $1 and you give me back 4. That's it. It all goes to the wallet. That's about it. Okay, so it's about time to finish. These are the resources. You get it's a really nice book, Mastering Bitcoin. I think one more is coming about Ethereum. I've got it has my GitHub here, and official BIP repository, and the SoftUni course, because we have a course here at SoftUni about blockchain technology. I assume there are no questions. Are there? Or? Okay, okay. Thank you for being here, honestly. That's awkward. Okay, let's stop the stream.